Okay, so because the weather is doing weird things and some of us may lose power temporarily or for long periods of time, who really knows anymore? This weather is a whole bunch of nonsense if you ask me. So I decided to record the discussion ahead of time just to make sure everybody will have access to it. I know, and I did one of these videos before, you guys said it was helpful, and I am doing my best to uh, make sure you have these videos to look back on and things like that, because I know chemistry, like I said, can be a little daunting at first, but I hope you guys are going to like it. And so far, you guys seem to be doing great. So today we're going to talk about molecules. So last week we talked about atoms. Remember, those are the fundamental units, basically, of matter. So when we're looking at matter, we can, we'll talk more about this as we go through, but so matter can be classified into, is it a pure substance, is it a mixture, and then, so mixtures are going to have more than one type of atom or something like that in it, and a pure substance is obviously going to have just the one substance in it. And that pure substance can be further then broken down to, is it just an element or is it a compound? So that's what I mean by what is the composition of matter? It's like what makes it up? Is it a pure substance? Is it an element? These are words that we will be using in conversation as we go through this unit. So get familiar with those. And if you need further clarification, I'll be posting some links if I can find some good things about useful YouTube videos that hopefully the school won't block, because I don't know what's going on with that either. Okay. So remember, quick review, atom is the basic building blocks of matter. An element is the substance that is only a single type of element or a single type of atom. So then we organize those elements on the periodic table of elements by molecular or by atomic mass and things like that. And that'll be the next discussion we talk about, is how do we organize this periodic table and why is it so cool? Okay, so then we get into molecules. So remember, elements are the basic form. Remember, we talked about how elements and atoms kind of be like interchangeable words sometimes. But when you put one or more of these atoms together, that is when you get a molecule. So if it's listed on the periodic table, it's a singular unit. If it is a molecule, it is a multiple unit. So if you look over here, examples of elements is like a single O for oxygen. That's an element. That's what you're going to find on the periodic table. It's represented by the symbol of O. Same with hydrogen. It's represented by H, and it's just one hydrogen by itself. But obviously we know oxygen is important to us. We breathe it in every day. It's really important for living. But oxygen likes to have a friend with it. Oxygen usually comes, at least in the form that we breathe in, it comes in the form of O2. So that means there are two oxygen atoms here. So that makes it an oxygen molecule. So remember, it's got a buddy there. And occasionally the ozone, which is the stuff that's in our atmosphere, it helps protect us from solar radiation and things like that. It's kind of important, but you wouldn't want to breathe it in because your body can't process this type of molecule. So this is three atoms of oxygen all put together. So for us, it's a slightly bigger molecule. So every time you add on to this base unit, this oxygen here, so every time you give another friend, it takes a slightly different form and it becomes a bigger molecule. So we'll talk about different types of bonds and things like that in a future discussion, but basically understand that when you put these two atoms together to make this molecule, they are bonded. And some bonds are stronger than others and things like that, but they're not just floating kind of in the same vicinity, so to speak. They're like actually together. Like if you put your hands together and you put your fingers overlap with each other, that would be like a bond. So we've used oxygen so far. We've got two oxygens here. That's two oxygen atoms to get the oxygen that we breathe in, that is O2. So you may hear me say some of these as shorthand. I might say O2 or H2O, things like that. Those are pretty common, so I would expect you to know that, but if you obviously need help, obviously ask me. So we've got two oxygens here to make ozone, but it's not always just two components or two atoms that are the same. So like when we have our water, we have H2O. I know we've heard this before. So this has one oxygen atom and two hydrogen atoms. So that gives one hydrogen or H2O molecule. So we've got three different atoms that are all put together here to get this H2O, which is the water we obviously know and appreciate. And then we have some other examples here. So like this is carbon dioxide. This is the stuff we breathe out. Remember we talked about the carbon dioxide being produced with the vinegar and baking soda reaction the other day. So this is how we would write carbon dioxide, one carbon and two oxygens. So again, they're different, but they are bonded together. So we have a carbon dioxide molecule. And then here is an example for sulfuric acid. You can see we got three different types here. We've got two hydrogens, one sulfur, and four oxygens. So these are ways, so there's, depending on the type of bonds and the atoms involved, there are limits to how many things can be added. But in this case, there's, four oxygens on top of this sulfur here. So one thing to point out is a molecule is the smallest unit of a material that can be divided into without changing the properties of the materials. So if, like on water, if we take away the oxygen, it's not water anymore, it's now just hydrogen. So if we break it down any further than this, it's not a molecule anymore, it's back to being atoms. And we just have an oxygen atom and hydrogen pair, which will probably be atoms as well. This is important because, like for those of you interested in space travel, we found deposits of frozen water on the moon. And this is important because, water is expensive to get into space, it's heavy, but obviously astronauts need it. And also they need fuel for their rockets and things like that. So the current idea is if we go to the moon and we start mining this frozen water, this ice that's usually found in the bottoms of craters where it's in the shadow and things like that, we can then separate out the molecules and separate out the atoms and essentially get some oxygen to breathe, and we can get hydrogen, which can be turned into fuel, or we can actually just keep it the way it is and use it as water. So water is very multi-purpose, and they are working on technologies that would be transportable to the moon or Mars or wherever, so that we could actually use these molecules and reduce them to other forms of atoms, or reuse them in other ways, so that we don't have to bring everything with us, because that is expensive and it is heavy, and it is obviously not what we want to do, because resources change, our needs change over time, so we need to have options. Back to molecules. Woo! Okay, so again, molecules form when two or more atoms are bonded together chemically. So remember, they can be the same atom or they can be different atoms. And the key thing here is they are sharing electrons. So electrons, remember, those are the things that we talked about, the components of an atom. So the electrons are the ones that are found in the orbitals or the shells. And when you're bonding with another atom, you got two atoms here bonding together. In this example, it's oxygen. So they are using what's called valence electrons, and that is the outer ring or the outer orbital, the outer shell, whatever you want to call it. That is where those electrons are located. So we can get to, oxygen wants to be stable. So O2 is a pretty stable molecule, and that's why our body uses it. So in this top part, we have two separate oxygen atoms. They are not bonded together. So let's count the valence electrons. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So there's 6 valence electrons in each of these outer orbitals on each oxygen atom, which is great and all. But to make it an oxygen molecule, to make it O2, these two valence orbitals, these outer orbitals, are going to come together, and they are going to share electrons so that each oxygen molecule will have a full outer shell. So that means, let's see, if we can, 1, 2, 3, 4, 5, 6, 7, 8. If you go over here, 1, 2, 3, 4, 5, 6, 7, 8. So they both have 8 electrons in their outer shell, their outer orbital, and that makes them happy. Molecules like to be happy because that makes them less reactive and things like that. So they are coming together, they're joining forces, and they're making this O2 molecule by sharing 2 electrons each, essentially, and they're forming this bond. So another word you will hear a lot is a compound. So you might have seen this in the real world. There's places called compounding pharmacies where they actually take special prescriptions that your doctor will write, and they actually make the medicine right there for you, as opposed to like a big pharmaceutical company, or whoever makes Tylenol. I think it's like Bayer or something like that. They have like big factories that produce all their compounds for them, and then they sell it, sell it to CVS or Walgreens, and that's where we buy it. But if you go to a compounding pharmacy, they actually make it there for you. So compounds are a chemical substance formed when 2 or more different elements bond in a specific proportion. So, in the previous example, both of these were oxygens. We're not losing any of the properties of oxygen here. We're just forming an oxygen molecule. But in a compound, it's going to form a new identity, essentially. So we're losing our individual chemical properties from our original atom that each gets coming together. So on this example, we take Na, which is sodium, and then you mix it together with chlorine, which is Cl. These are their periodic table identifiers. So sodium on its own, it's highly explosive. It's a hot mess. You don't want to mess with it. It's very, very bad. And chlorine, also very, very bad to mess with. It's a poisonous gas. It was used in, I think, World War I. So, when we're looking at, if we don't even look at this stuff down at the bottom, we're looking at explosive solid and poisonous gas. They're going, why would I want anything to do with that? That sounds dangerous. Well, if you put these 2 together in a new compound, a new molecular situation, you get NaCl. And that is common table salt that I bet is in your house right now. Or you can get the salt that, we're kind of dealing with Snowmageddon right now. So, if you see on the news, they're putting salt on the roads. They are, you hear all these words about salt trucks and things like that, and you see salt on the ground outside the school so you don't slip and fall. That is what this compound is. It's salt. So that's why we use it. It's got really good properties. It makes our food tastier, and it also keeps us from sliding off the road. So completely different properties than poisonous gas and explosive solid, but because of how these 2 are bonded together, because of how they shared their valence electrons, we get salt. Science. It's wild. It's crazy. So chemical bonds are when we share or exchange electrons. And so remember, a molecule is the smallest unit. So in this particular example, this is how we get water. So we remember water is written as H2O. So we start with 2 hydrogens and 1 oxygen. Right now they're separate. So when they're by themselves, they're both gases. They don't conduct electricity. There's not a whole lot of exciting things to talk about there. It's hydrogen and it's oxygen. Woohoo! But if you bond them together, so you can see the different colors, they use different colors to show the different valence electrons that are being shared here. Because oxygen wants to have 8 valence electrons. So if you bond these together to where you get H2O, and also if you notice, it looks like an upside down Mickey Mouse. So that's another way you can remember H2O. It looks like a Mickey Mouse. This new compound is a liquid that conducts electricity. And when I say conducts electricity, I mean, this is like why when there's a lightning storm in the summer and you're out swimming, you get out of the lake or the pool or whatever it is, because, if say you're swimming in the lake, lightning can strike on the other side of the lake and you could still get shocked because of how much of a great conductor water is for electricity. We don't want you to get hurt. So that's why when there's a storm coming, I say, get the heck out of the water. because water conducts electricity very well. You know, that's why you don't mess with down power lines, things like that. So we went from two completely separate identities to one new compound, one new identity here. So here's our Mickey Mouse guy again. He's still upside down. So remember, we started with 2 hydrogen and 1 oxygen, which is great, but we can't just write out, because in some of these molecules you'll get, you know, S8, like sulfur 8 or something like that. And that's a lot of S's to write out, and nobody wants to read that. Nobody wants to do that. Like, yeah. I'll tell you from experience, scientists are kind of lazy. We want everything to be shorthand. It's just how we are. You know, there's acronyms and things like that. But so when it comes to chemistry, we write out chemical formulas. So it makes our lives easier. We don't want to write out 2 H's plus an O because that's more effort than it needs to be. So we use a subscript. I know this is harder to do on Google Chat and things like that. So when I was having you guys look up chemical formulas on Google the other day, I wasn't that picky because I understand Google Chat it's more difficult to type in subscripts. But in a perfect world where we're not using Google for everything because I can see your beautiful faces in front of me in the classroom, like say you're writing this out on paper, you're going to put the 2 a little bit beneath the H. So that way we know there's 2 of this H and only 1, because the 1 is implied, of this oxygen. And you put them all together and you get H2O. So a way to look at chemical formulas is you can call it a recipe for a chemical substance. Just like if you have grandma's favorite cookie recipe, you want to follow that recipe so you get the exact cookies. If you don't follow the recipe, like if I decide I'm going to put H3O, well, that's not water. So I'm not following the recipe. So I'm going to get something completely different. And if you're not sure exactly what is in this recipe, you can read the chemical formulas and it'll tell you the number of atoms of each element. That's what this subscript here is for. So if you're not familiar, so sub means below. So that's why we kind of put it like down a little bit. So if you see down here, we've got a C plus a C plus an O. So take a second and think, what is C1, C2 plus O? What does that mean? How should I write that? So remember, C is carbon and O is oxygen. There are 2 C's. So we're going to put the 2 as a subscript. So we're going to put C2 and then an O, C2O. That would be this particular chemical formula or this particular recipe for this molecule. So chemical equations, like I said, we can use them to shorthand things so we understand how many atoms are going into these molecules, but we can also use it to show how we're combining other more than one set, basically. So this one only got us 1 water molecule, okay? That's great. We need more water molecules. So we can use coefficients, which are numbers that go on the outside. They're written like regular numbers. They're bigger, so you can see the difference in the sizes here. We've got a subscript, we've got a coefficient here, and this tells us how many of these particular sets we're putting together with this set so that we get, in the end, we get 2 water molecules. Because remember, the coefficient comes over. Just like in your math property, in your math classes, you learn about how numbers can carry over. That's basically what's happening here. So there's no coefficient in front of Mr. Oxygen here. He's kind of lonely. He still has a subscript, so we know there's 2 of him. So we know he's the breathable oxygen molecule. But there's no coefficient, so that just implied to be a 1. So in this particular equation, we start off with 2H2 plus O2 yields. That's what this arrow means here. It means yield or gives. The result is whatever methods of words work best for you, but yields is a word I will use a lot. 2H2O. So the final result is 2 water molecules, as you can see by this lovely picture here, 2 little Mickey Mouses. So we start off with a total of if you can also multiply these two, this gives you 4 hydrogen atoms. So if you count them 1, 2, 3, 4, 4 hydrogens, and this we know is 2 oxygens, 1, 2, and then when they all bond together, we get 2 water molecules. So we talked about in the initial slide, there's a word called a pure substance. So what is a pure substance? How do I know? What is going on? So a pure substance, it has a definite and constant composition, meaning it's not changing. It can be an element or it can be a compound. So it can be an element or a molecule. But what it's made out of is going to be the same no matter where you look at it or when you look at it. So if you have like a big flat dish of some kind of some substance, if you pull from the left, it's going to look exactly the same as if you pull from the right. So it's completely pure. It's the same all the way across the board. It is pure. Just like if you ever, talk about, pure water, it doesn't have any gunk in it, right? But not pure water, like if you go get water from a pond or something, it's going to have some other stuff in it. So it's not entirely pure. So you can see the element here. Remember, pure substances can be an element or a molecule. So we have just all pure hydrogen here. And here we have all pure element of oxygens. These are oxygen molecules because there's 2 of them bonded together, but it is still pure oxygen. It's a pure substance. Now this down here, this is water. Water is, if you only have pure water, then yes, it would be a pure substance. But if we were to split these molecules, then we would not have a pure substance. So in comparison, there is a mixture. So a mixture is not pure. So they give the example of a trail mix as an example for a mixture because you can pull from here to get an M&M, pull from here, I think that's a raisin, over here it's like this weird peanut thing. All of those are different. Those would all be different types of atoms in our molecular mixture. So it's not a pure substance. So this thinking, words are hard, guys. So not chemically combined. So they're not all bonded together like in a pure substance molecule. And so it's not going to change the separate properties of the separate parts. So the M&M is not going to suddenly become a raisin or a peanut or whatever else is in this trail mix. Another mixture example I like to point out is chocolate milk. If you make it yourself, not the stuff you buy that's already pre-mixed, in the gallon or whatever. If you take chocolate powder and mix it in milk, that is a mixture. That's why we use the word mix. If you mix it really good, it looks like it's a pure substance. But fundamentally, you still have cocoa powder and milk. And if you were to separate those two out very painstakingly, mind you, it's considered a mixture. Chocolate milk, obviously, once you mix it up, it's very, very hard to separate out, but it could be done. Just like with this trail mix, you could sit here and count out 1 M&M, 2 M&M, 3 M&M, and then 1 peanut, 2 peanut. Nobody wants to do that. We're just going to grab a handful and eat it because it's trail mix. But in certain chemicals, compounds, we don't want mixtures. We want pure substances. It just depends on the type of lab work you're doing. So this is just a quick overview of how molecules are cool and how they work. We'll have some question and answer time coming up in a day or so. Like I said, I wanted to have this review for you guys ready to watch on your own because who the heck knows what the weather's going to do in the next couple days? I don't know. I just know it's gosh darn cold and I am not a happy person. So I hope you guys are staying safe and warm. If you need me, please get a hold of me. If there's concerns at your home, like if you're worried about not having enough food to get through this awful cold spell or something like that, there are resources to help you guys. So please do reach out. It's a no judgment zone. You know that. I love you all. Stay safe and let me know how I can help you.